we're looking at vibrations, and this time we're going to work in some air drag or some kind of damping force and see how that affects things. First, let's see if we can predict what it's going to do. In the example I have here, I've got some block, some mass M. It's on a spring, and we're going to take it and we're going to pull it off to the right. And then after we pull it off to the right, we are going to let go. So plang, it's going to bounce, oscillate back and forth around the equilibrium position. Let's see if we can make a graph of what we think it's going to look like. If I graph the position as a function of time, first let's make a graph of what it's going to look like before we add in any air drag. Okay, so we start up here at some position, maybe 2 meters. So when time is 0, I start up there, and then it's going to oscillate back and forth. And I think, like we learned last class, we're pretty sure it's going to be some kind of sinusoidal oscillation, and you can go and figure out what the period of that would be. Okay, what if we add in air drag? What's it going to do? Okay, so if I add in some drag or some kind of damping force, I think you can maybe guess it's going to do something like that. It's going to start off oscillating, but the oscillations, their amplitude is going to get less every time. So the peak here is going to be less than the peak when we started, and the peak of the third oscillation is going to be even less, and then the fourth oscillation even less. So there's going to be some shape that's going to be governing how this oscillation is going to shrink with time. Now, if you added a lot of air drag, or like a tremendous amount of damping, then you might see that it never overshoots at all. It just kind of comes down and gradually approaches. Whoops, I did not mean to. Let's try that again. If you add a lot of too much damping, or if you add a lot of damping, then it'll never actually overshoot. Okay, so this would be the equation for a lot of damping. Okay. All right, let's see if we can take a guess at what the equation for this damped oscillation would be. And again, here I'm going to go back to this this graph right here. Let's see if we can guess what that equation is going to look like. Well, it's going to have some sinusoidal function. So we might guess like some kind of sine equation. And I think we're going to have to multiply it by some function that's slowly getting lower and lower and lower and tapering off to 0. Okay, can you guess what that function is going to be? Okay, maybe you guessed some kind of decaying exponent, like e to the negative something. Something like that. So if you guess that, you'd be right. So this equation's we kind of know the answer in advance. So if we get something that we don't like mathematically, it's good to have good to be able to identify a definitely wrong answer by having some guess of what it's going to do. All right, let's now move on and look at the math here. All right, first let's identify the forces. We've got some forces in the vertical direction, but there's no acceleration, so those will just add up to 0. And we've got some forces in the horizontal direction. We've got the force of the spring and the drag force. Now I drew the drag force to the right. Of course, if the velocity is positive, then that minus sign means that the drag will be to the left. And if the velocity is negative, that minus sign means the drag will be to the right. Okay, so F equals ma. So we've got our forces. Spring force, drag equals acceleration, which is 2 derivatives of position. Put all the terms to one side of the equation. This just makes it look kind of like something you've seen in your differential equations class. And And then we'll look for solutions which have a form a e to the st. Now, you might be used to calling it a e to the mt, but here I want to avoid the m because we have an m that represents the mass of the object. So I want to avoid some mass confusion. Bad joke. Okay? All right, so now plug this in. This is our form of the solution for x. Plug that into this equation and try to solve it for values of s. Go ahead and try it out. So pause the video, try it out, and then once you've got your answer, start watching again. Okay, the answer you should have gotten is you're basically, when you plug in and solve for s, you'll get this quadratic equation. And if you didn't get it, ask me on today's meet. So we've got two values for s, so we plug those. Remember, this came from assuming our solution was a e to the st. So if I've got two numbers for s, we've got one solution, a e to the s1t and b e to the s2t, where these are the two values we have for s. Okay, now there's two possibilities. Either the s values will be complex or they will be real. So if they're real, we just move on to the next step, meaning that if there's no imaginary piece to them. If they're complex, that means the values of s will take a form like something plus omega times I. And if we plug that into when they take that form, you're going to get a pair. You'll get like negative 2 plus 3i and negative 2 minus 3i. So they're going to come as a plus or minus omega I. So plug that in for s into our equation, and you can pull out an e to the b from both terms. So pull out that e to the b, and then you're left with this a e to the I omega t and b e to the negative I omega t. You can then bring in Euler's relationship, substituting e to the ix for cosine x plus I sine x. You did that in your math class, but you can never do it too many times, so you should do it and show that you can rearrange and get e to the something times sines and cosines. Notice that this is the form of the equation that we would have guessed. This is what we were thinking that it had to look like. Okay, now regardless if the solutions were real or if they were complex, you now have to find the constants either a and b or c and d. And to find those constants, you'll use your initial conditions. So in our case, the position when time is equal to 2 is 2, let's make it 2 meters, and the velocity when time is 2 is equal to 0. Now note that velocity, you might think, hey, wait a minute, that's a trick. There's no velocity in those equations. Well, just remember that velocity is x dot. So you can take a derivative of the equation and plug that in to get a and b or c and d. And we'll do an example when you get to the meet. All right.